Hello everyone, it's me, Billy Younger again. I'm working Oscillations Example 6. This is a multi-step example where we apply basically the principles we learned from simple harmonic motion, simple harmonic oscillation. And let's go ahead and get started by showing you the question by sharing my iPad screen. The spring shock suspension system of cars obey Hooke's law when people get in and out of the car. A 1,195 kilogram vehicle gets 3.05 centimeters closer compared to the empty car to the ground when four people, total mass M equals 325 kilograms, sit in the car. What is the apparent spring constant for a spring we can use to model the car's suspension? B, how much closer to the ground, again relative to the empty car, would the car be if 205 kilograms of people sat in it instead of the previous larger mass group? C, when the car's shock absorbers are worn out, see Buck's car in the movie Uncle Buck, they allow the car to bounce up and down through more than one whole cycle. If the car has a mass of 1,195 kilograms and has 325 kilograms of people in it, at what frequency in cycles per second or hertz does it oscillate? Finally, part D, what is the period of oscillation? So this is a pretty straightforward problem as long as you realize it is simple harmonic motion so that we have a very specific definition of omega. We can also say that the position as a function of time would be given by x of t is equal to a cosine omega t plus phi. In this case, though, we're not asked to study any of that. We're really just asked various things about the spring constant k, as well as the angular frequency omega, the regular frequency f, and the period t. So let's get started. Solution. What we're making use of here is the fact that omega is equal to the square root of k over m. And remember that comes from any differential equation that is x double dot equals k over m times x, or excuse me, x double dot plus k over m times x equals 0. We also know that omega is equal to 2 pi times the frequency. We also know that the frequency is 1 over the period, and for that reason you could also say that omega is equal to 2 pi over the period. We also know that F is equal to negative kx, which is Hooke's law, but in this case we're going to be working with the magnitude so that the minus sign, which is really important for setting up the differential equation, but is essentially irrelevant when we're talking about magnitudes of k, magnitudes of x, or magnitudes of force. So let us start off with part A, which is what is the apparent spring constant? So what they told us was that 1,195 kilogram vehicle dropped 3.05 centimeters closer to the ground when 325 kilograms of people got in it. So that means our force F is 325 kilograms. And of course, that's the mass, and we know that the mass leads to a force called the weight, which is W equals mg. That's another expression we're using. I didn't write it down because it's pretty self-explanatory, or hopefully we know it by now. But either way, I'm just going to write 9.80 meters per second every second. So that will be the actual force when I multiply 325 times 9.80. That gives me 3,185.0 newtons, and this is consistent with me keeping two extra digits beyond the significant digits. So the 3,100 and quote 90, 3.19 times 10 to the 3 would be the actual force. Now we use F equals kx. We're going to say 3,185.0 newtons is equal to K times X. And in this case, we found that the X was 3.05 centimeters, and that is 0.0305 meters. So notice we did have to put it in to the SI base units. From this, we can figure out that K is equal to some number of newtons divided by meters, and it should be 3,185 divided by 0.0305, which is 3 sig figs divided by 3 sig figs, and this gives us 1.04. There's another 4, and then I'll leave a space for a 3 because these last two digits are not sig figs, and it's times 10 to the fifth, and that is in newtons per meter. So that is our actual spring constant, which is what we were asked for. Again, I've carried two extra digits beyond the significant figures. Now we'll start with part B, and part B says, what if instead of the 325 kilograms of people, we put 200, and where's the quantity? 205 kilograms. I can't even find it on my paper. Oh, there it is. So 205 kilograms. So now this time the force is going to be equal to 205 kilograms times 9.80 meters per second every second. And that gives us 205 times 9.8 gives us 2.00, and then I'd say a 9 followed by a 0 newtons, and that's, well, actually, I should go ahead and put it in scientific notation, so I don't want to put the unit on the air yet. So I'm going to say 2.0090 times 10 to the 3 newtons. That's the force. Again, we're going to use F equals kx, and this time we know that k is the 1.0443 times 10 to the fifth newtons per meter. So we can use that to actually find out what x is. So in this case, we're going to say 2.0090 times 10 to the third newtons is equal to 1.0443 times 10 to the fifth newtons per meter times x. That's just the F equals kx. Again, I've dropped the negative because we're just concerned with the magnitudes at this point. And from this, we find that x is equal to, I divide the 2.009 times 10 to the third by 1.0443 times 10 to the fifth newtons per meter, and that just gives me meters, and the quantity is 0.0192, and then carrying two extra digits would give me a 3, or excuse me, yeah, it would give me a 3 and an 8. And that's meters, so we're going to say x is equal to 1.923 centimeters, and that's the answer to part B. Now that we've done that, we can go to the next part. It says, this is part C. When the car's shock absorbers are worn out, they allow the car to bounce up and down through more than one whole cycle. If the car has a mass of 1,195 kilograms and has 325 kilograms of people in it, at what frequency in cycles per second or hertz does it oscillate? So now I'm going to do part C. And part C, what we know is omega is equal to the square root of k over m. Now, the square root of k over m can be worked out because we already know what the k is. I just got to figure out what the mass is. So the k is 1.0443 times 10 to the fifth newtons per meter, and then I've got to divide all of that by the total mass, which is going to be 1,195 kilograms plus 325 kilograms. You can see that when we add these two numbers, they actually have all their digits are significant. So when we add them, they'll be good all the way up to the ones place, and that includes basically 4 sig figs. So it'll be 3 sig figs divided by 4 sig figs, and then we take the square root of that, so the answer should come out in 3 sig figs. So now that I do that, I'm going to go ahead and first compute what's under the radical. So 1.0443 times 10 to the fifth. I'm going to divide that by parentheses 1195 plus 325 close parentheses, and that gives me the square root of 68.7. And now I'm going to add two extra digits, 0, 4. Those two are not significant figures. And notice that the units work out to be newtons per meter is a kilogram per second squared, and then I divide by a kilogram, so that's just a reciprocal second squared. So I'll put, in this case, s to the negative 2 power. So when I take the square root of all that, I get 8.28. So omega is equal to 8.28. That's my 3 sig figs, but I'm also going to add two extra digits, and that's going to be a 8 followed by another 8, and that's in radians per second. So that's the angular frequency in radians per second, but what we want is f. And we know that f, since omega is equal to 2 pi f, f must equal omega over 2 pi. So if I take that omega and divide it by parenthesis 2 times 3.14159, that gives me 1.319, and then the next digit is a 2, and that's in hertz, which also is the same thing as cycles per second. So the frequency in hertz, or cycles per second, is 1.32. And that's our answer to part C. Now, for part D, we want to know the period. So for part D, we want to know T equals question mark. What we know is omega. This time I'm going to do it symbolically as opposed to just plugging the numbers in. What we do know is omega is equal to 2 pi f. And we know that f is 1 over t. So we know that omega is equal to 2 pi over t. Therefore, we can say that t is actually equal to 2 pi over omega, but omega is the square root of k over m, so we're going to say t is 2 pi times the square root of m over k. Notice I had to turn over the quantity under the square root, and that gives me t equals 2 times pi times the square root. Now we're going to take our mass, which was 1,195 kilograms plus 325 kilograms. That gives me 1,520.0 kilograms. In actuality, I just underlined it as if that first zero is a non-significant figure, and that's not correct. So I went back and fixed it. The next digit 0 as well. That's why I didn't bother putting any more on it. Now I'm going to divide that by the spring constant, which is 1.0443 times 10 to the fifth newtons per meter. Now we've got a kilogram divided by newton per meter. That's going to become a kilogram meter over a newton. Newton is a kilogram meter per second squared, and if we divide a kilogram metered by that, we're just going to get seconds squared under the square root. So when we take the square root of it, we just get seconds, which is exactly what we expect for the period of oscillation. So I'm going to take 2 times 3.14159, and I'm going to take and multiply that by the square root, And then inside of the square root, I'm going to say 1,520 divided by 1.0443 times 10 to the fifth newtons per meter. That gives me 0.758. That's all our sig figs. And then I get two extra digits that I like to put on these. And that's going to be a 0.3. And that is seconds. And that's the period of oscillation of this car with really poor shock absorbers. So I hope that helps. This is just another example of all the different equations you can use. This isn't taking into account, for instance, the fact that you can also know that the velocity is omega times a, that the acceleration is omega squared times a. Those are things that we can also use once we know that something's obeying simple harmonic motion. So, where a, by the way, is the amplitude. So, anyways, I hope that helps and have a good day. Bye bye.